Uh, Very good afternoon, everyone, and I welcome you all to our. Yeah, good afternoon, all. I welcome you all to our center on World Quantum Day. So today, on World Quantum Day, April 14th, we celebrate the fascinating world of quantum science, the foundation of technologies that are transforming our future from quantum computing and secure communication to advanced sensing and precision measurement. The date 4.14 symbolizes Planck's constant, we all know, um, a cornerstone of quantum mechanics. This day is not just about science, but about innovation, collaboration, and inspiring the next generation to explore the quantum world. Uh, on this short note, I would like to thank you all for joining and coming to our center. And then I would request our Dean of School of Natural Sciences to say a few words about our center and to start our program. Thank you.
Okay, so good afternoon and welcome to CQuERE, Center for Quantum Engineering, Research and Education. CQuERE is part of School of Natural Sciences, which is part of TCG CREST deemed to be university. The School of Natural Sciences has many other centers. It has Chinta, which focus on neurobiology, RISE, which focus on sustainable energy, FTSI with a focus on nutrition, and CARE with a focus on cancer cure. So all these centers have a active PhD program, and incidentally, tomorrow is the last date to apply. So some of you who are still interested, you can still apply. Okay. So, and apart from that, actually we have a school of mathematics and computer sciences. That center, I mean, that school is launching a master's course on artificial intelligence from this year. So some of you who are, as you know, AI is right now looks like the future, okay, at least in next few decades, right? So some of you may wish to apply in this course, okay? From next year, some other centers will also be launching master's courses, which you may again be interested in. CQuERE will launch a course on quantum computing, master's course. RISE will launch a course on energy materials and devices. And Chinta will launch a course on neurobiology. Okay, so I will suggest that you look forward to launch of these courses, and you may want to spread the word. If anybody is interested, please look at our website for announcements and look forward to, we will look forward to you even joining us in these courses. Okay, so apart from these courses, I think today we are going to celebrate the World Quantum Day. And this day is to celebrate and to promote the quantum technology in general public. And as some of you may know, or some of you may realize, the second half of this century is most likely to be a quantum technology oriented. This half is artificial intelligence. Next half is likely to be more quantum technology. So you will get a glimpse of this future today from the talk of Professor Bhupendra, as well as by visiting our laboratory, looking at the posters, and just talking to people here and there. Okay. So we will get a glimpse of what may happen for second half of this century. Okay. So welcome to this quantum world day and future of quantum world. Okay. So thank you.
Thank you, Agarwal. Uh, Now I would request Professor Bhupendra Nath Deb for his next talk. But before that, I would like to just briefly say a few words about him. He is currently leading the quantum computing experimental activities at CQuERE TCG CREST on superconducting qubit-based systems. So I would request Professor Deb to say few things and start your talk.
Can you hear me at the back? Okay. Good afternoon. So, are you ready to celebrate World Quantum Day? Okay, let's go ahead. You see the title of my talk, The Quantum Leap from Laboratories to Everyday Life. And this program is for general public actually. So general public will not know much about the laboratories, but about the life, everyday life. They are enjoying lots of fruits of quantum science. So they should have a link between the laboratories and quantum science and the gadgets they're using. So that's the idea, and that's how I'll proceed. So laboratory gives you observation. It's actually experimental laboratory. So the laboratory is the nature. What you observe from the nature, that's also laboratory. And from these observations, we try to formulate theories to understand the laboratory results. Right? And that's where the in-between part is the understanding through the development of quantum theory in this particular case. And once you understand quantum theory, then you can apply those theories to develop gadgets. That means technology. That's the last part, from science to technology. So I'll just show you the connection between all these things as I go along. So World Quantum Day, of course, this is launched in 2022. And that year also there was a Nobel Prize in quantum. It's a quantum entanglement, right? But next year, the 2025, had an added celebration. It was completion of 100 years of quantum mechanics. That's International Year of Quantum Technology. So this year, 2000, has a further additional things with it. 2025 Nobel Prize was also given in the area of quantum mechanics, quantum science. So that was in December. So after that, this is the first quantum day, World Quantum Day. So we have several significant things behind us, and we are celebrating 2026 as a more special World Quantum Day celebration. So I'll first give a brief milestone of the development of quantum physics, and then what we have learned from quantum physics and how that knowledge was used to develop quantum technologies. These two are separate. I just go parallel. Science and the technology side by side. So World Quantum Day, you have already known that it's more than 65 countries together, they decided to observe World Quantum Day, and this was officially launched in 2022. And quantum physics is the most fundamental theory. We have to describe the nature at the level of elementary particles and forces that constitute the universe. The next line is important. The universe speaks the language of quantum physics. The universe speaks the language of quantum physics. So modern lifestyle comes close to quantum physics. And without quantum physics, you would not have had mobile phones, laptop, GPS, your Google Maps, etc. Magnetic resonance imaging in the hospital, lasers, all these things you would not have had without quantum mechanics. Let's look at it. This is anywhere in India. This blacksmith is doing this, and this is glowing here. To understand this, it was very difficult. It was not understood till the end of the 19th century. So what you see here, something like this, they had a temperature list like that. If it is too bright here, it corresponds to something like that. So it's related to the temperature. You notice that this gentleman is holding somewhere. That means that place of that rod was similar to temperature of his body temperature, right? It's not burning. And there's not much light coming from there. So depending on the temperature, this light was coming. So experimentally, what was done, you can put a spectrometer and try to analyze what are the frequency components, what wavelengths of light are there. And if you do that, and you plot the intensity as a function of frequency or wavelength, then what you get is this one. Too sensitive. So this is the one that you have there. You know that spectrum shape is changing on the temperature. And this temperature is something like solar temperature on the sun, and maximum radiation is coming in the visible range here. But the shape is this, but classical theory predicted the shape should be something like that. Now, somehow the pointer is not showing on the screen. But anyway, right. So classical physics predicted this, which means that if you go to shorter and shorter wavelength, you are supposed to have an infinite intensity, which is not correct, right? So this is also called UV, ultraviolet catastrophe. If you go to the ultraviolet regime, the intensity shoots up to infinity, but that's not right, ultraviolet catastrophe. And then this gentleman, that Max Planck, actually made a very drastic assumption, like maybe the emission happens in quantum, discrete energy. It's not a continuous energy, discrete energy packets. With that assumption, is that this energy in that packet is given by h nu. Nu is the frequency of light, whatever, right? And this was the assumption. With that assumption, you could explain this observed shape of the spectrum. And so h is called the Planck's constant. That's right. And what's the value of h? We know that it is this. The pointer is not showing on this screen. Yeah. The pointer no, this is not. This pointer is not showing on the screen. The pointer. Huh? You can see the pointer? Oh, I cannot see that. Anyway. Okay. So this is the value of h in Joule second. If you take the unit of energy as eV, electron volt, that value comes out to be this. Somehow I cannot see. For that I use this one. So this is the value. If you round it off, it becomes 4.14. And if you write the American style, you write the month first. It is the 4th month, April, and the 14th day. That's how it is celebrated. April 14th as the World Quantum Day. So now we see that all the discontinuities in nature are given in units based directly upon h. So earlier it was not known that it was thought everything is continuous in nature. But now we see that energy is delivered or absorbed in small packets. It's discrete, it's not continuous. So it appears explicitly or implicitly in every equation in quantum theory. So from now onward, when you go to quantum theory, you'll find that this H appears everywhere in quantum theory. And this is a new revelation about the aspect of nature. So this discreteness about the nature is perceived through this work. So the journey of quantum science has just begun from this. Now, as I said, that the universe speaks the language of quantum physics, right? Here I have put a spectrum of that, not the universe, a part of the universe, subset, is the solar system, say, starting from the sun. Sun, here is the photosynthesis, enzyme, how it works, even the DNA, everywhere something like quantum tunneling that takes place, right? All of that. So this is the language of quantum physics. That, as I said, universe, I have taken a subset of universe. It speaks that language. Now I'll come back to those things later. Now, celebrating 100 years of quantum, that last year was the International Year of Quantum. And this is what in editorial of Nature came, quantum mechanics 100 years on, an unfinished revolution. So 100 years is not really, you haven't completed. It's unfinished, and there's a lot to go ahead in our future. And what is the importance of that? A century ago, physics had its Darwinian moment. You know, the Darwin, without Darwin, you wouldn't understand the modern biology, right? So we want to understand the universe, understand the functioning of nature. So that's why it's called the Darwinian moment of physics. So the World Quantum Day, of course, amplifying diversity in quantum. World Quantum Day joins Quantum 100, that was last year. Now, to celebrate this World Quantum Day organization, they also introduced some Quantum City Prize. It's a participation from different continents. And last year it was won by an Italian city for their work or their display. I just mentioned it. So this was something they, in the city square, they displayed with Mars model to represent something like quantum superposition, entanglement, all this, to take it to the public. So general public without even learning physics, so that they can appreciate, because they should appreciate, because they are enjoying the benefits of quantum physics in everyday life. So the timeline of development of quantum physics, let's look at it. 1901, of course, entered Planck's constant, we have just discussed. 1905, light is the stream of particles that the Albert Einstein showed through his photoemission experiment, right? And then the major thing came in 1913, Bohr's model of atom. And 1922, atoms of quantized spin. The concept of spin didn't come at that time. Electron spin was not known. But through the measurement of the magnetic moment of silver atom, they put the concept of spin there. Purely experimental, theoretical knowledge didn't come at that time. So let me look at some of these developments following this timeline. So this is the photoelectric effect. You know that if you have a piece of metal and you shoot light, and electrons comes out from that, right? And the energy, kinetic energy of the electron is given by energy of the quantum of energy minus something called the work function, right? Now you notice that if you shoot orange light, each quantum has 2 electron volt energy. If you shoot violet light, each quantum has 3 eV of energy. Now say work function of this material is something like the 2.3 eV. Then what an orange quantum will do? It doesn't have enough energy to reject it. So no photoelectron emission. Violet light will do that, right? Now that's the physics of it, that what do you get in technology? In toilet, automatic flash, that works basically using this principle. There, of course, you don't have ultraviolet or something, they use infrared, it's a 940 nanometer. But what happens that when the reflection from your body of that is detected in the detector, that sets the current flow, that makes an actuator to flush. So the quantum physics of that we are enjoying even in our toilet, right? Now next we go to the Bohr model of atoms. You all know about the Bohr model of atoms, hydrogen atom, that, right? So the electrons can only have discrete energies. Again, the discreteness comes, right? It's not continuous energy spectrum. Then this hydrogen emission spectrum, that was an example that was already there in the laboratory, but there was no explanation for that. So using now Bohr's model, one can show that if you have electrons in orbit from a higher orbit, if electron transits from this higher orbit to lower orbit, there is an energy loss, right? That loss goes out as a photon. So for this spectrum, when you take this, you have these lines, and each of these lines you can explain this n equal to 2 to n equal to 1 gives you red light, n equal to 4 to n equal to 2 gives you green light, and even a higher one gives you blue and then violet. So all this whole spectrum of the hydrogen discharge lamp could be explained with Bohr's model. And before that model came, there was no explanation for these observed effects. What is the technology we are enjoying? Our fluorescent light, even this, right? This has mercury vapor, mercury light that emits mostly in the UV. And there is a fluorescent material coating there that can emit all three components that gives you white light, right? So from the Bohr model, we can still get this explanation for that and the development of technology. So there are many deficiencies of the Bohr model. For example, it's good for hydrogen atom, but for mercury atom, it won't be applicable. There are major flaws. So, but fails for atoms with higher atomic numbers. It failed to explain Zeeman effect or Stark effect. You already read those things, but I'm not going into the details of those. The Bohr model cannot explain those. And it cannot explain the intensities of spectral lights. Whatever the, you can identify these different frequencies, but the intensities of the spectral lines, Bohr model cannot explain. So there had to be more improvement in the model. So 1916 Bohr Sommerfeld model, that's an improved model of Bohr model. That could explain something more, but still it was not complete. Deficiencies of that model as well. All these things that belongs to the old quantum theory, whatever we discussed. So old quantum theory was improved now, that giving us the new quantum theory. As I mentioned, that 1922 atomic spin had been shown, but the concept of spin theoretically didn't come at this time. But then 1925, the major development happened, the matrix formulation of quantum theory. So this is the beginning of the new quantum theory beyond old quantum theory. So this is, as you read here, after his famous trip to Helgoland, Werner Heisenberg derived the quantum energy level of a one-dimensional oscillator in terms of physical quantities, such as transition probabilities, that could in principle be measured. Three fundamental papers by Heisenberg, Max Born, and Pascal Jordan developed the first consistent formulation of quantum mechanics. So this is the mathematical formulation of quantum mechanics that came. Where is Helgoland? It's a North Sea small island here. And I happen to live in Hamburg and work there in Daisy. And every summer I used to drive to the coast of Northern Sea. North Sea. North Sea means North Sea. And then one sabbatical, I also stayed nearby, not worked in Hamburg, but stayed in Pinneberg some area. And Helgoland belongs to the district of Pinneberg. Perhaps I can legitimately claim that quantum mechanics was discovered in my district. I was resident there in that district. Anyway, this is a small island, and Heisenberg went there to recover from his hay fever. What's the matter? It's actually two islands. Just a small island, population less than 2,000. So that's where the quantum mechanics were developed. So after 1925, the same year, the wave-like behavior of matter. Light, of course, was the wave that was known long back, but then it's also like a particle that became evident from Max Planck, and then Einstein demonstrated that. But Louis de Broglie thought that if light can behave like matter and wave, why not matter can also behave like matter and wave? He just put forward this idea, theorized this idea, but then that was experimentally proven in 1927. But the idea that it can behave like a wave, that prompted Schrödinger to formulate his wave equation for the matter. So Schrödinger, in 1926, he formulated the Schrödinger's equation. And since people were familiar with wave and wave equation, Schrödinger equation actually grabbed the whole community, that they can easily proceed with that method. So you know all this Schrödinger equation, time dependent and time independent. And if you find the solution psi for a particle, you're solving the Schrödinger equation, you can actually derive all the behavior of this particle. Oh. Okay, so now let's look at the big particle and the small particle. What are the differences in that? Big particles is the classical, right? With the classical mechanics, we can describe all its behavior. But that is a big particle if you reduce it and come down to an atom. Can you describe the behavior of an atom with classical physics? The answer is no. That's where come in. So after you have released an atom, say for example, you cannot predict either the position or the speed accurately. The atom violates classical mechanics. So here comes the Heisenberg's uncertainty principle. If you want to measure the position of the atom or the speed of the atom, you cannot do it precisely. There's an uncertainty in the measurement. Whatever position you measure, there's an uncertainty. It's not absolutely sure about the position. And Heisenberg's uncertainty principle tells that this uncertainty in position, uncertainty in momentum, this product is always greater than this. It cannot be zero. So this is always larger than that. So the behavior of small particles like atoms or electrons are governed by quantum mechanics, and they are called quantum particles. This cartoon tells you that if it's a basketball, if you know its initial speed and know the direction, you can precisely calculate where it's going to land, right? But if you carry out this experiment with an atom, you cannot predict where it's going to fall. Something like for basketball, you can say it will fall at the center, but for the atoms, it will land anywhere around that. You can precisely tell it will land there. But you can find the probability, with what probability it will land at which places. And we'll find that with maximum probability, it will land at the center. This is what you can predict. It's not a deterministic theory. It's a probabilistic. So then in 1927, it's understanding the wave function. When Schrödinger solved this wave equation and found the value of the wave function, he didn't know what it means actually. So his Max Born came with an idea that it's actually the Max Born provided a probabilistic interpretation of Schrödinger's wave function, stating that the square of the amplitude mod psi square, that gives you the idea about the position of the particle. So the interpretation of the wave function came from Max Born. And of course, Schrödinger's equation did not have some other things, didn't have the spin in it, right? So it could not explain some other behavior of atoms. So then came the Dirac's equation, relativistic equation, that took spin, and that also predicted the existence of antimatter, just from the equation it automatically comes. So this is how quantum mechanics developed. But now, since we are going to relate quantum mechanics and its fruits to modern life, that very important contribution is the 1929 quantum description of solids. The Felix block solved the problem of if you have a solid, you have a periodic arrangement of atoms, right? How the electrons would behave in that. That solution came from Felix block. Let us look into that. So this is the, say, hydrogen atom. If you take, this is the atomic potential 1 over R. And from the solution, you know that these are the energy levels, n equal to 1, n equal to 2, n equal to 3, all these things for one atom. Now I have one hydrogen atom here, another here, another here, another here. That means I'm repeating the atoms. That's what my solid is, right? Atoms are repeated. So what picture do I have? This is like one atom here, one atom here, one atom here, one atom here. So the potential is like that, right, for this system. So Felix Bloch proved a theorem that allowed the description of the behavior of electrons in the periodic structure of crystalline solids. And his theory offered the basis for the concept of electronic band structure. So now we know materials, some of them are metallic, some of them are insulators, some of them are semiconductors. From where? From the band theory of them, right? Semiconductors have band gaps, metals don't. Insulators have larger GaN bands. To understand the solids behavior, without this contribution from Felix Bloch, we could not have understood those. So with that, the quantum mechanics provided an understanding of the properties of semiconductors such as silicon, germanium, etc. And with semiconductor, this was the first transistor that was invented in 1997 in Bell Labs. So already some workable things that has been produced from the understanding of quantum mechanics of materials like semiconductors. So that's the beginning, birth of the first quantum revolution. The mobile you are holding in your hand is about 1 billion transistors now. So that would have not come without the understanding of quantum mechanics of materials like semiconductors. This is one of the supercomputer in Oak Ridge National Lab. This has tens of billions of transistors in that. And what is its operation capability? Flops means floating point operations per second. 1.2 exaflops, exa is 10 to the power 18. That many operations it can do in 1 second. It's a supercomputer. It came from that understanding of quantum mechanics of semiconductors, right? So that's how the quantum science has affected our life. Let's proceed a little more. You have this device, it came from quantum mechanics, right? You have GPS system that's also came from the quantum mechanics. So this is a 24 satellite constellation, and each of them has cesium-133 atomic clock. First position of the grandfather's clock is 1 second, 1 tick, right? And this one ticks this many times per second. That means of the order of 10 to the power minus 10 seconds it can measure, right? And how does it give you a GPS map, Google map? It has to measure, say you are standing there and the earth is rotating, your mobile is also rotating with that. And it can directly see these red ones, red connected ones, those satellites it can see. So it measures the distance of your mobile from that place, from the satellite. And if 3 or more can measure the distance, it can locate you exactly where you are. But if the precision, your time measurement is bad, it will show you are sitting here, but your GPS will show you are sitting somewhere in Bihar. Right? If you don't have the time resolution, that's why this time resolution is very important. It is coming from, again, quantum mechanics of atoms, right? So these are the quantum technologies we are enjoying because of quantum physics. Another quantum material is superconductors. Superconductivity was discovered in 1911. And 1957, quantum theory of superconductivity was given. It's called the BCS theory, Bardeen, Cooper, and Schrieffer theory. And superconducting materials are quantum materials, basically. And from that, Superconductivity is that something like that. It's a material that's resistance is zero. If you pass a current through that, there is no loss. I square R is the loss, right? R is zero, so no loss. So it can come on forever. It's 100,000 years that current can flow through that, right? So that's one property. Another property of superconductor that it repels magnets. So if you have a material, because if you heard about high TC superconductor, room temperature is not superconductor. Magnet sitting with nitrogen on that. At that temperature, the high TC superconductor becomes superconductor. Soon as it becomes superconductor, it will repel the magnet, right? So this is another property, and that has been transformed into technology, which is like in Japan, Yamanoshi superconducting maglev train. It's a flying train. It's through magnetic levitation. It doesn't touch the track. It's away from the track, and you see that speed of that is so high because there's no friction basically. So that's what you get the technology from superconductivity. Let's look at this another one, magnetic resonance imaging. Without quantum mechanics, we would not have had that. So 1925, the spin of electron was discovered. That's still theoretically. But in 1930, these three gentlemen actually measured the magnetic moment of proton. Electron spin, this is electronic magnetism, right? Electric magnetic moment. But proton also has a magnetic moment. That was measured there. Now, in any magnetic field, if you put a magnetic spin, magnetic moment, it will start precessing, right? Oops. That starts precessing, right? It's a particular frequency. And employing this, you can cause a resonance transition. That's called the nuclear magnetic resonance. So for your brain, it's a proton environment that is imaged. So it is basically this magnetic moment. This causes the magnetic resonance. That's what you are doing. But the problem is that today you get a very beautiful picture of magnetic resonance images, right? That would have not been possible without superconductivity, because the magnets that is available is not strong enough to do that. But if you make a superconducting magnet, you can make a very strong magnet, make a coil of superconducting material, there is power loss, and you can pass a very high current, so you can produce a very strong magnetic field. And that's what it is inside this. That is the magnet is provided by coils within that. So two quantum phenomena, superconductivity and magnetic resonance, they are providing you this magnetic resonance imaging. So without quantum mechanics, we would have not come to this level of enjoying these benefits. So let's come back to the Schrödinger equation. Now we know that you have a potential here, V, right? Now if you plug in different kinds of potential in the Schrödinger equation, you get a different solution, right? And from that solution, you understand the behavior of particles in that kind of potential, right? So you have different kinds of potential. You have already studied some quantum mechanics. You know that you step potential, infinite potential well, finite potential well, potential barrier, delta function potential, all these things you have solved and got the solution, right? Now, thing is that when you just solve and get the solution, you have done only algebra. You haven't done quantum mechanics you haven't understood the science of it. So you have to go a little to see what they mean, solution, and only then you can extract the benefit out of that. You can apply that technology. So this is a infinite potential well or a particle in a box model. This is a finite potential well. This is a step potential well, step potential. This is a potential barrier. So different kinds of solution you get if you plug in this kind of potential in your Schrödinger equation. Okay. Okay. So this potential, it's infinite potential well or the particle in a box you have solved. And what you got, the energy levels are just like this, right? So depending on the value of L, if L is infinity, energy levels would be touching each other almost, right? If L is small, the differences between E1, E2, E3 would be this way, right? So that's what this predicts, particle in a box. Now, imagine that you have a very large particle. That means L is large. So energy separations would be small, right? Come to a small particle, L is small, the energy separations would be larger. Say, for example, this is E1 and E2. Now, if you have a semiconductor, for the electrons, you have this potential in the conduction band. For holes, you have this potential in the valence band, right? So this would be like state in the conduction band. This would be like your discrete states in the valence band, right? So in a bulk semiconductor, you can get a transition from electron from the conduction band to valence band, right? So what would be? This would be the energy difference. If you get a photon out, that will have this much of energy. But if you have something with a small link line, and there are electronic states here. If the first one available is here. For the whole state, first one is available here. So the transition will give you this much of energy, much larger energy, right? That means emitted light color would be different. So that means now by controlling the size of your semiconductor structure, you can control the emission wavelength, right? So that's the physics that you learn. And this picture shows that mighty small dots. These are small dots of silicon in a solution. But the colors are different. You see that this is red, green, and blue. What's the difference? This size is about 6 nanometer diameter, and this size is about 2 nanometer diameter. This emits in blue, this emits in red, in between size emits in green, right? So now, some of you probably have in your house quantum dot TV. Here there's a quantum dots, the screen has quantum dot, and that gives you a sharp image, and also the combination of different colors coming from there. Now, of course, the importance of that I cannot explain in just in. It's a whole Nobel Prize was given for the discovery and synthesis of quantum dots, 2023. Now, by chemical methods, you can produce a large number of them, and quantum dots also, with that you can investigate, you can do the diagnosis of certain disease within the human body. You can also treat, directed drug delivery, all these things you can do. So quantum can give you so much of technology beneficial to common public. Now I showed the potential that is confined from all the directions, this side, right? But you can confined in one direction only if you make layers like that. How do you do that? Let's say this material here, aluminum gallium arsenide, this has an energy gap larger than gallium arsenide, which is in between I have put in. So here the band gap is this much, and here the band gap is this much. Here it's the same material, band gap is this much. So that means if an electron is there within gallium nitride, gallium arsenide, it fills the potential wall on the two sides, right? And it is confined in one direction. But the other two directions, electrons freely. Yes, it's one direction. But that has also many useful images. So in this case, if you make something like this and make a PN diode with that, when you excite an electron, it comes here because that is the lower energy. When you excite a hole, it comes here, that's the lower energy. So your recombination of electron hole happens within that. So you can get a more intense emission of light. So with that you can make a quantum dot, quantum well laser. It is called quantum well. First one I described the quantum dot. So this is how the transition is going to be from here to here. So corresponding to this energy, that the color of this light. So you can tune that. If you make the size smaller, then this energy level would be higher here, there. So the transition will produce a different light, right? So you can produce laser with whatever energy of the photons you desire, just by restructuring your device by the side. Now, if you make many of them, instead of just one of them, just you make many of them like that. Now we see that this a quantum dot or a quantum well behaves like an artificial atom, like atoms of discrete energy levels, right? So each of them is an artificial atom. Now what you have put many artificial atoms side by side. So it is like your solid crystal, right? It's an artificial solid. Here also you can get electron, the electron wave function here, if you look at it, since it is finite potential, its wave function is not zero at the wall, it penetrates, right? So that means in that region where the wave function penetrates, it can overlap with the next one. So that's how it can actually form a band, just like a solid. And so these are called mini bands. So each of these energy levels can form bands. But other than that, this is your potential. What can you do with this potential? So it's a potential if it is like that, right? If you apply a battery here, negative on this side, positive on this side, so these potential curves will go up there and down there, right? So if you do that, you can make this tilt in the potential. Now, if you inject an electron from this side, and this electron can transit from here to here, emitting a photon. And through this thin barrier, it can go to the other side. And taking advantage of the electronic band there also, it tunnels through and this one. In this one, again, it can emit another electron by undergoing transition from here to here, another photon. So if I make this structure with 100 wells like this, single electron can emit 100 photons. Imagine. And here I can also tune the energy by tuning this size. I can make this differences between these two different. So the emitted photon energy I can tune. And this is called the quantum cascade ledger. Earlier I just made quantum well ledger. This is called the quantum cascade ledger. And this has an enormous tunability. Starting from, say, go to infrared to far electromagnetic waves you can generate with quantum cascade ledger. And this has lots of applications in that. For example, this is the wavelength, say 100 nanometer to 10 centimeter. In this wavelength, you can get electromagnetic radiation with this ledger. And some of them, if you have large molecules, their absorption bands are very close. So to cause an excitation or an emission, detect an emission, you don't have appropriate ledger, but you can make quantum cascade ledger. So that's you can even detect explosives, which are large molecules. Explosive, you can intense ledger, you can fire to the plane to make communication system damaged. Lots of applications are there. I cannot explain all of these things because there are many applications. You can do spectroscopy of large molecules with that. Oops. Okay, so all the quantum technology discussed so far belong to the first quantum revolution. When did the first quantum revolution start? After the invention of transistor. And then all the things I explained, that came from first quantum revolution. Here, the whole power of quantum mechanics was not exploited. And now let's go a further forward, and let's see the second quantum revolution based on two other apparently very strange quantum phenomena called superposition and entanglement. These two phenomena were not used for the first quantum revolution, but the second quantum revolution uses this, which is not very old. It's about 2 decades or so. Let's see that this superposition and entanglement, those two are very strange ideas, but they are real. They work. What does superposition mean? Let's look at this. Solve this hydrogen atom problem. We know that ground state, the first excited state, next one is there, right? But if you take an hydrogen, can you tell exactly where that electron is? Is it n equal to 1 or n equal to 2, n equal to 3? You cannot, right? Because probabilistic, you have some probability of occupation of n equal to 1, some probability of occupation n equal to 2, n equal to 3. So basically, the electron, the atom is occupying all energy levels available. So we call it that electron is in a superposition of all those states. Similarly, the position-wise, can you tell where the electron is? N equal to 1 orbit is somewhere here, n equal to 2 is somewhere here. So you don't know. So it is at both positions. So a quantum object can have multiple positions at the same time. It can have multiple energy levels at the same time, right? So that's the superposition. Now, oops. So if we can actually choose to work with two levels. There are many, but experimentally figure out something so that we can work with two levels. So it's a superposition between two states. Right? So superposition between two states is written as like alpha 1 state 0 so beta times this. This is called the probability amplitude. Alpha square plus beta square equal to 1. Total probability has to be 1, right? Now it is in superposition, but if you want to measure it with some experiments, it will collapse into one of the states. Right? Where is Biplab? Demonstrate your superposition. Here, start. Two states. What do you see? It's a bird in a cage, right? It is like a measurement. When you make a measurement, it collapses into. No. What is this speedily? This is just demonstration of superposition. So meaning that the superposition state is actual, but when you measure it, you can get only one state. It will collapse into one of them. Well, since you cannot see the superposition, you can call it illusion. You cannot directly see the superposition. That's difficult to believe. It's difficult to conceive these ideas, but it really works. That's what tells us indeed it was in superposition.
Different state.
This is in this case two different states. But as I mentioned, multiple states also can be there. But from now onwards, we'll work with two states for the future quantum technologies. Now, say one electron I'm talking about in superposition, simultaneously they can be at both places or at two different energy levels. That's the meaning of superposition. So in 1940, very early, this cartoon appeared in this New Yorker magazine. So this man thinks that, well, this person has gone two legs on two sides. Well, so it is in superposition. It can take two paths if you don't observe it. When you observe, you cannot see it. So early in 1940, this cartoon appeared in this magazine. So now, classical and quantum, what is the difference? If it is classical, then electron can be either here or here, right? But in quantum, it is not either or. It is at both places simultaneously. At any moment, it is at both places. That's the super difference of the quantum system. So this is the superposition, but what does it mean? The electron is in superposition until it is measured. What happens when you insist on that you want to measure and find out in which box 0 or 1 the electron is, right? So measurement is actually an interaction with the quantum system, with the measurement device, and it causes the collapse of the superposition into one of the states. But if you cannot tell which one, this happens randomly as the probabilistic things happen. If I throw a coin, I cannot tell whether it will land with head or tail. It's probabilistic. So if that in the coefficient alpha and beta equal to 1, then roughly probability is half and half, right? 50%. But if you throw a coin one time, it will land with either head or down. You cannot interpret that. You have to throw, say, 1,000 times. Then you'll find roughly 500 times head, 500 times. So it's a probability. So here also for quantum measurements, if you want to get the right answer, you have to carry out the same experiment millions of times. So this is strange, but it is real. So if you find it difficult to conceive this idea of superposition, even the greatest scientist Einstein had problems and he didn't believe it. He said, do you really believe that the moon is only exists when you look at it? Otherwise it is not there. So he didn't believe. And he also made a comment. Oops. God does not play dice. For example, here it's a probabilistic dice. So this is the quantum proponent. This is Einstein. God does not play dice with the universe. Tells him, the Einstein, stop telling God what to do. That is the nature. You don't have any control on that. You have to try to understand it. Now, what is entanglement? The next idea that is difficult to conceive. Now, if we have two quantum systems, now this one can be in a state of 0 or 1, 0 and 1, rather superposition. It's 1 also, right? So now if we have two, I can have 0 here, 0 state. I can have 0, 1. I can have 1, 0, 1, 1, right? These are the 4 possibilities. So these two quantum systems together, they can have this 4 possible combination. So it is in a superposition of these 4 states. Now, I can write it then, if it is superposition of these 4 states with the appropriate coefficients. Now, if I say that beta and gamma equal to 0, the probability of occupation is 0, then I am left with this. And this represents a special type of correlation. So this is first one 0, second one 0, first one 1, second one 1 state. This is a special type of correlation. But if I want to explain mathematics, it would be very difficult to conceive. I take a picture, I use a picture to explain it, what it is. Think of this eagle, and when the eagle's wings are down, I call it 0 state. When it is up, I call it 1 state, right? In this particular case, either it can be 0, 0 or 1, 1, right? And it's a superposition of these two. It cannot be like this. Eagle cannot fly like this, right? So this correlation is not there. So that's like the middle 2 term 0 in the earlier zone I showed. So this is one kind of correlation. 0, 0 plus 1, 1, superposition of these two. Either this or this possibility, superposition of those. And mathematically, this is called a Bell state, which is written like this with equal probability. 1 over square root of 2 whole square is half. This is half. Mathematical definition is called the Bell state. So this is the one kind of correlation. Let's look for another kind of correlation, which is this one. When this is 0, this is 1. When this is 1, this is 0. So it can be this two superposition. So here it cannot go like this, right? So this is another kind of correlation. So these are called entanglement. Superposition and correlation. Superposition was just superposition. Now entanglement is superposition plus correlation. And both of these are used in modern quantum technology, in the second quantum revolution. This is also called another Bell state. Mathematically, it's written like that. So about entanglement, what did Einstein say? Calling it a spooky action at a distance. Why did he say that? Because this correlation, like if the wings of this eagle extends up to the infinity, even at that distance, we would know that if it is 0, 0, if this one is 0, this one is 0, I have to measure only one. Without measuring, I will know what is the state of the other, even if the distance is infinity. So that's why it says that it's a spooky action at a distance. He didn't believe in this either. He was the opponent of both these ideas of quantum mechanics, superposition and entanglement. And it was unfortunate that he was such a scientist. Which one?
Entanglement taking place. Entanglement taking place. Is it a mathematical verification or experimental verification?
Both are there. I'll come to that. So this is around 1935. So the half of the scientific community supported Einstein, half of the concept of Bohr. So it didn't progress much. But then one gentleman, Bell, came with the Bell inequality and to verify whether entanglement is correct or not. And then successive experiments came. And then finally, entanglement was demonstrated experimentally. But before I go to that, this was the explanation of Schrödinger about the superposition and entanglement. Imagine I have a cat here. This is two halves of this box. This is inside a box. These two halves, I can either close this one or that one. Here, I have radioactive atoms. It's a detector that can detect whether radioactivity has occurred, emission has occurred. If it occurs, it releases this hammer and it hits this flask, glass flask, which has poison in it. So the poison will fall and this cat will die. If this has not emitted any radioactive particles there, then nothing will happen, cat will be alive, right? So here the atom, that has two states. It has either emitted, either decayed or not decayed, right? It's a superposition of these two states. So that's one quantum object, say. And the cat is live and dead. You don't know which one. It is another quantum object, but there is a correlation between these two, right? Upper one, lower one. So even without looking at the lower half, say this is locked. If I just look at this one, whether the atom has decayed, I immediately know the cat is dead, right? So I don't have to measure the other one. So if I know the result of one, if there is entanglement, I can tell what's the result of the other one. Other one immediately collapses to the corresponding state with which it is entangled. So superposition is the ability to simultaneously exist in multiple states, and entanglement is the ability to exhibit connection between particles despite large physical distances. Okay, so these are the three gentlemen who actually got the Nobel Prize in 2022 for demonstrating entanglement between photons. And this demonstration is so convincing that this is the two islands, Canary Islands, of the coast of Africa. They have one setup in one island and 143 kilometers away another setup. And using quantum entanglement of photons, they have transferred one quantum state from this island to the other island. That's called teleport. So this is what is entanglement verification at the ultimate. So Nobel Prize was given for demonstrating that. And that is used in quantum communication today. So what the distance is, right? So now let's go back. I mean, since we are dealing with two states, say these two sides of a coin. It's a 0 or 1, that's classical. And quantum, it would be superposition of these two, 0 and 1 simultaneously. If you have two coins, this is one, this is another, they can be entangled, right? This is the concept. So how the computers work, let's see. So this is the basics of computer. Information is stored in 0 or 1, is basically a transistor, which is either off or on, 0 or 1 state, right? Now through that, you can build up that the supercomputer is shown. It's basically a transistor. but it's classical. It's working with that principle. Now imagine I have 3-bit transistor. That means 3 transistors, 3-bit quantum system. It can be 0, 0, 0, all the way up to 1, 1, 1, 8. But out of one combination of these 8 can be stored at a time, right? But if I have a quantum bit instead of the transistors, then each of them can be 0 and 1 simultaneously. So with this combination, all the 8 numbers, I'll be able to store at the same time, at every moment. So my power of information storage goes out exponentially, is 2 to the power 3. If I have 4 bits or qubits, 2 to the power 4. That's the storage capacity, that's how it goes up. And let's see how the operation goes up. Say, for example, I have Alice in Wonderland, a maze like that. And this ladybug at the center is trying to find the exit. So, for example, if it goes first time here, it's blocked, right? So it has to try many times to find its exit. But if I have a colony of ants here, and all of them can explore in different directions, it's like a parallel operation. It's a superposition if I have, all the states can explore all the possibilities. So this will exit faster. That's how the quantum computing is so fast. This is the number of qubits. Exponentially, the speed goes up, and linear, if it is transistors, classical computers, it goes up linearly. So that's how we can get, in quantum computing, the speed up. And this is a quantum computer. It's a 53 qubits only, but we have tens of billions of qubits in supercomputers. So they have shown it's a superconducting quantum computer, and they have calculated something with 200 seconds, and then they estimated that at that time the largest computer would have taken 10,000 years to do the same calculation. Next version in December 2024, they have used slightly larger, it's 105 qubits, and they have carried out one computation in less than 5 minutes, and they have estimated that at that time, whatever supercomputers are available, that would have taken 10 septillion years, 10 to the power 25 years. What's the age of the universe? 10 to the power 10 years, right? So that's whatever possible, that would be possible with quantum computers. So quantum computers are poised to reshape our world by addressing the complex challenges we face today. Oops. How does one implement a physical qubit? That was superconducting qubit I just casually mentioned. We'll go a little bit more in detail. Of course, the obvious choice is an atom. Atom is a quantum system. This size is sub-nanometer. Atom is. Now I can use a quantum dot like that. That's a collection of atoms, but still size is small, so that it behaves like atoms, discrete energy states, right? And discrete wave functions here that we see. Also, I can use to implement a quantum bit, a qubit. Also, I can use micrometer scale quantum system, that is superconductors, that later. There are other possibilities. You can use an spin, electron spin, photons, NV centers. There are many possibilities. So how do you make a quantum computer using superconductors? That's the macroscopic, something we can hold in our hand. We cannot hold atom in your hand. So now I come back here. The universe speaks the language of quantum physics. So I need to pick up some words from this vocabulary of the universe to go into that superconducting qubit. So here they do quantum tunneling. The sun produces energy by quantum tunneling. It's the two protons via quantum tunneling fuse and emits energy there. And everywhere else I showed that the quantum tunneling is taking place. So from the vocabulary of the universe, we pick up these two words, quantum tunneling. Who are Harry Potter's fan? You know that Harry Potter's tunnel through this wall, right? So these days at the station here, this King's Cross train, this is kept there. So people go there to take pictures. But I hope if they try to tunnel, they will break their heads, right? But we know that the small particles, not big particles like a person, small particles can tunnel through small barriers. So this is the quantum picture and classical picture. The slide, it has to jump out, it cannot tunnel, but if it were a quantum particle, it would tunnel through, right? So let's take an example. If you have a wire like this, you connect to battery, you have current flow, right? If there is a break in the gap, will there be current flow? Most of the people will say no, but the answer is yes and no both. If the gap is large, there won't be, but if the gap is small, electrons can tunnel through that gap and there will be current flow. And of course, that has been, if it is quantum particle, it can tunnel through that. And this is the quantum mechanics problem you have solved after Schrödinger equation. Now, if I have a barrier here, what happens? I put the barrier, I see that beyond the barrier, I have some probability of penetration of the particle, right? That's how the electron can tunnel. If the barrier is thin, you can get a current. But this is not just theoretical, it happens. And one of the major technologies has been made using this quantum tunneling phenomenon. That's the most powerful microscope. Here, if you have a surface of any material, you bring a tip of a material, and electrons can, using that, you can get an atomic image of the surface of this material. And this is an image of a silicon 111 surface. Each white dot is a silicon atom. This picture was done with scanning tunneling microscopy. USB flash memory within this quantum tunneling takes place. Here is a robot holding a drill gun that is also using a material called quantum composite, and that quantum tunneling takes place with that. So it has gone into technology in many different ways. Now, for a superconducting quantum qubit you want to make, it is basically an electric circuit, like an LC circuit. So you know that LC circuit also quantum, you can make a quantum oscillator out of that by tuning the value of L and C. But its energy levels are equally spaced. But if you replace this L with a Josephson junction, that gives you a nonlinear inductor. Josephson junction is like that. Two superconductors separated by an insulator, which is like a potential barrier. The Cooper pairs are the current carrier in superconductor. So Cooper pairs can tunnel through this. And through this tunneling, the Josephson junction works. So that is basically a superconducting qubit. And in order to work with the lowest two energy levels, you need to ensure that you cool down to near absolute zero temperature. That's what this machine does. It's called dilution refrigerator. We cool it down to minus 273.14 degree. This is the absolute zero. Just 0.01 degree above absolute zero. The junction that I showed. Now that temperature you need to ensure, because you know that if you have many states, even an atom, your Boltzmann distribution tells you the probability of occupation of each state. If you lower the temperature, then you can ensure that you are occupying only the ground state. Because I just showed that you want to work with two states. If the other states are occupied, it will not work like my qubit. But these three gentlemen got the Nobel Prize last year for showing discovery of macroscopic quantum mechanical tunneling. Microscopic system, it happens, but it's a macroscopic system. It's a Josephson junction you can hold in your hand. It's macroscopic. Quantum tunneling happens there. And for demonstrating, got the last year's Nobel Prize, 2023. And this same circuit, John Martinez, he was involved in the development of this quantum computer of Google, the first one, using this superconducting quantum computer. So this is an IBM quantum computer. This is this what is a refrigerator, dilution refrigerator. This is the dilution refrigerator in our lab here. Oops. So this is a Lanussian refrigerator. Inside it looks like that, 10 millikelvin, which is the temperature I mentioned. It was with 1 qubit earlier experiment. Now we have a 5 qubit processor, quantum processor. We are working with that. Anyway, so there, the interaction session, they can learn more about this. So the applications of quantum computer, medicine and materials, drug discovery, it will help in that. Banking, finance, artificial intelligence, communication, cryptography, logistics and supply chain, military and defense, everywhere these applications are there. So there's a big future ahead of us using quantum technology. Now I tell you slightly about the quantum sensors. Our center also works on quantum. Think about that, the sensitive measurements of acceleration due to gravity. Exploration. Now what is that? If you have say the force between this Earth and a small object here is given by this, right? And you know that this force is also mg. But now the question is that if you have something liquid here underneath, say it is oil in the ground, right? What will happen now? This formula gives you R. R, distance between this center of this Earth and the center of this mass, right? But actually it is not the geometrical center. It's actually the center of gravity, center of mass, right? But if you have, this is here, and if you have oil, the density is much less, right? So your center of mass will be shifted on this side. So your R actually is larger than the center of mass. If R is larger, the force is smaller, so your G is smaller there. So if you measure the acceleration due to gravity there, it would be small. Of the other height, if you do it here, then this R is small, then G would be much larger, right? So by measuring G at different places, you can explore where there is oil or where there are minerals, all these things, right? So this is, how do you measure G now? Of course, this is a very simple pendulum. You get the time, and from this is measurement of this period, you can get G. You can, from the falling body, H, if you measure, is half gt square. You measure the time. And height, you get value of T. And then also you can do it a spring mass system. Is the how much it will hang. If its weight is less, it will be short. If its weight is more, it will be longer, right? Weight is what? mg. So if G is large, it would be longer. If G is small, it would be shorter, right? Just by measuring the length, you can do it, right? But these are crude methods. But you can use quantum approach, quantum gravimeter that measures the gravity. Use quantum objects like free falling atoms to measure gravity with very high precision, about 1 microgal. 1 gal is 1 centimeter per square centimeter, 1 centimeter per square second. So here, this kind of measurements are going on, experiments, all that. Diamond looks good, it sparkles, right? But there are defects. Diamonds with impurities float to perfection. That means so beautiful colors of diamonds you can get, and they have defects. But the defects are important. For quantum, if you have a defect like this, it's called the NV center. So these are the carbon atoms in diamonds. If you can remove 1 carbon atom, you have a vacancy, right? Next atom, you can replace a carbon by a nitrogen. So that's the nitrogen and vacancy just nearby. That's called the NV center. The carbon atom is bonded to 4 nearest neighbors, right? So each one contributes 1 electron there. But if 1 atom is missing, then 3 electrons are hanging there, they cannot bond. And if a nitrogen that has 2 additional electrons there, 5 electrons are there. It's called the NV center, new center, but it can also have collect 1 electron from surrounding. So 6 electrons forms the NV minus center. And that behaves like this is localized in that area. That behaves like an atom, like say a carbon atom, right? 6 electrons. It's a 1s level, 2 electrons, 2s, 2 electrons, then other 2, right? Similar things happen here. You have up down electrons, the last 2 electrons are here. And this is parallel here, spin 1. Excited state, if you excite 1 from here to here, still it is 2 parallel, this 1. So this spin means it has a magnetism, right? So if you put it in a magnetic field, it will respond to that. So this response, through this response, you can actually find out what is the strength of the magnetic field. So magnetic field sensor using this. So you'll have another lab here in our doing this kind of work. Then I described this Josephson junctions, right, between two superconductor and insulator. If you have two Josephson junctions in a ring like that, it's called a squid. Now, if I send the current from this to this, it splits equally on two sides. But if I apply a magnetic field through this loop, that will generate a current preferentially in one direction, right? So these two won't be equal anymore. So from this disbalance, you can estimate what is the magnetic field strength. And we can determine it to extremely high precision. You can even get auto Tesla, 10 to the power minus 8 Tesla. Right? So this has other ramifications. Like, for example, magnetoencephalography is imaging of neural activity in the brain. Because of the ionic electric signal, there's a magnetic field there. And that you want to measure. It's extremely small. It's of the order of 100 Tesla. You can measure it with a squid device like that. So you have met with many squids there, different places, and you measure with that. So that's how superconducting quantum magnetic sensing. So some liquid helium is here, and then with this, the head is put there. And that's how we can do the imaging, because there are many squid sensors around here. And this is good for many diagnosis, epilepsy diagnosis, autism, many other kinds of patients are there for the diagnosis. Investing about 10 to the power 100 femtotesla, extremely small field. So with squid and Josephson junctions, you can do that. So we are also trying to build these Josephson junctions in the lab. Yeah. So now, whatever I have discussed here, the second quantum revolution gives us quantum computers, quantum communication, quantum cryptography. Quantum communication, I have one shown there and through the entanglement, right? Quantum cryptography, when you get a message on your mobile from a bank, you see that 128-bit encrypted. This encryption means that the sender and the receiver only know what it is. Nobody should be able to intercept. But these are classical, they can be intercepted. But you can have quantum cryptography, then nobody can intercept that one anymore. So in quantum, I showed that also will advance quantum materials with newer technological potential. I didn't discuss about the quantum materials. That's another broad area. There also you have many different possibilities. So we have a bright future ahead with quantum. We have left 100 years behind, but we don't know how many 100 years we'll be developing new things using quantum mechanics. Thank you for your attention. Questions you can ask.
The quantum communication, in that, I heard one story and from internet that one person, living person, heart of him, some idle force is missing, consciousness is missing, because in physics, dead man and living man, what is the basic difference between these two? It's absent. Till today, it is absent.
Yes, consciousness is a topic. Some people think that it's a quantum.
Quantum.
It's still debatable. Consciousness is addressed.
Heart of death. There should be one communication between the soul expands and soul is going apart. Somewhere in the universe. Okay, no matter what is the distance. So that way, the connectivity is there. Then it will establish immediately that the soul exists.
Yes.
This kind of metaphysics.
It's a metaphysics still, but people are trying to understand consciousness in terms of quantum, but it's still debatable. We don't have any answer yet. Pardon? Good. You understand the principle of superposition now. Because entanglement was directly used to do that. Without using entanglement, they could have not teleported the quantum state from this island to other island. Pardon? Yeah, you can use teleportation to communicate the quantum state from one place to another. But for quantum communication, there is something called the QKD, quantum key distribution. So it's like if you have read about this Sherlock Holmes story, Adventures of Dancing Men, the code, right? That is breakable, but it's not. Now the code is generated using quantum principle, the quantum key distribution. So that is this, if I want to send something from to you, first I generate a code, and then I send this code to you. Through that only you will be able to read that. So there are different ways of quantum communication. No. It's different. There is no entanglement involved in that. Quantum tunneling is a simple tunneling process. Well, as I said, that this tunneling, the quantum physics have shown that the amplitude of this it goes like e to the power minus kx, right? So if x is large, then nothing remains. So it's the thickness of the potential barrier that's important for this tunneling process. Pardon? Second part I didn't get. Mass sensitive. It's in this case the mass of the quantum particle, but that doesn't enter anywhere. It comes only in the expression for energy, the k. K has 1 over 2m within the expression. Pardon? Yeah, I'll explain once again. Yes, it says the slide is whether
shareable.
I think it has been recorded. It will share somewhere.
Is it available in the YouTube? Yeah. Oh, okay. Then it's okay.
Okay. So this is you know that this bonds are this is tetrahedral bonding in diamond, right? So one carbon is bonded to 4. So if I remove one carbon from there, so then these 4 neighboring atoms, they are contributing 4 electrons that will be hanging around. But now one of them I replace by a nitrogen. Nitrogen has 5 electrons. So that will contribute 2, and the 3 will come from 3 other carbons. So 5 electrons are there. So it can collect another electron from the system. 6 electrons is the NV minus center. And these 6 electrons are localized. They don't go anywhere like that. So localized means this is now similar to say carbon atom. 6 electrons are there, right? But the nomenclature of the orbitals are different because carbon is isotopic potential. Here the potential is 3-fold symmetry, tetrahedral. That's why nomenclatures are different, but the occupation is similar. 2, 2, and 2 layers. The last 2 are now parallel here, both in the ground state and the excited state. That gives you spin 1. So then it is sensitive to the magnetic field if you apply magnetic field from outside. So you can measure the response of this spin, and through that you can estimate what is the magnetic field you have applied. And very weak magnetic field you can detect with that. No other question? Well, no extra development in the concept there yet. Who knows? There may be steps coming in the future.
conditions engulfing the whole universe.
Yeah, since we are speaking the same language of the universe now. Yeah, whole universe. This is quantum. As I said, the whole universe is quantum. I just took one sample of the solar system. And in solar system, you have so much of quantum. The energy is produced through quantum tunneling, right? And then when the sunlight falls on the leaf, photosynthesis, it actually, one photon is absorbed, one electron hole exciton pair is produced. And that hops within this leaf to a place where this reaction center is there. And there the actual reaction takes place, providing carbohydrate and oxygen release. That happens there. Within the enzyme also, even the superposition principle is there. And I showed the DNA string, and there's a proton tunneling can take place from one strand to the other. If that happens, the genetic code changes. That's the reason for our aging and also tumor, etc. It's a quantum again. No, this about 2 nanometers is the separation between the DNA strings, two of them. Photosynthesis, of course, it can happen because this tunneling goes from small hops. It's not one hop, because exciton, without energy loss, it can go quite a large distance within that. No more question? Okay, then probably I go to the last part, just to give a glimpse of what is happening in our center. Okay, this one we have to change. Sometimes it doesn't work, sometimes 3 or 4 together. Okay, the research program at our center, that I just give a glimpse of that. I will not go into the details anymore, any of them. One is theoretical quantum computing group. We have not talked much about that. So basically, the Schrodinger equation is there. And this is about the development of quantum algorithms. And there are different kinds of algorithms. Quantum selected configuration interaction, variable quantum eigensolver, quantum annealer eigensolver, quantum phase difference estimation, all these things they do. And they apply this to calculate electronic energy levels of atoms and molecules, etc. But eventually the target about the aim of our center is the translational research, to go to something that will be useful for the society. Things like you can use this optimization things for developing a model for traffic optimization. They want to go from here to Howrah. What would be the most beneficial route? Yeah? At this moment, yeah, that this should be able to do that. Financial market also, it could be add valuable things. Discovery. So today, you to develop a drug, you can do simulation with classical computers. Say 1 billion molecules you have tried, and you say that try these 1 million molecules in the laboratory. So you have to, in the laboratory, you have to test those. With quantum computing power, these numbers should be brought down to say 1,000. So you have to try only 1,000 in your laboratory. So your drug discovery process would be much faster. Because you can do a super massive calculation you'll be able to do. So through the calculation, Classical computer reduced billion to a million, and quantum computation will be able to reduce it from a billion to 1,000. For example, materials. Today we have superconductors which don't work at room temperature. But imagine if we had superconducting material at room temperature, then I can make our transmission line electrical. Pardon? That's what your quantum computation will be tell you what materials is suitable to give you superconducting material at room temperature. These are the things that one hopes that quantum computers will be able to provide. There are many practical things that is material science also. First one is of course like that. So I'll not go into the details of these things, but they're led by Professor Anu Pratap Das, who is the director of our center, and Professor Prasanna. So you can also talk to them about that. So these are the areas that I just mentioned. They work on those areas. Then also fault tolerant quantum algorithms. One thing I didn't mention, that quantum systems are very fragile. Classical bit is a 0 or 1, it's a transistor. If you turn it off, it will remain off forever. If you apply some voltage to get one state, it can remain forever. So information can be stored almost forever. But quantum system is very fragile. For example, the quantum computer I showed, that can have about 20 microsecond time. Within that, you have to finish everything. So the noise problem is there, the error prone. So error correction and fault tolerant algorithms, those are the things that are being developed here. And Professor Pankaj Agarwal does the quantum information and quantum communication. So these are different areas: quantum communication, quantum correlations, quantum cryptography. I just gave it 5 flavors: quantum foundation, quantum thermodynamics. All these areas you're working, theoretical areas. Oops. Another colleague is working on the application of tensor networks in various fields of quantum. That is through the network, the tensor network, that you can apply it to quantum chemistry, quantum communication, more or less all the possible things. Those are pictures for this quantum network.
Quantum network.
This is like even if you have many qubits in the quantum computer, what is the best possible way you can connect them, for example? That will be the faster operation of that, similar things. And of course, there is the quantum network for communication also there, but tensor network usually does the first thing that way. Quantum sensing with photonic integrated circuits and nitrogen vacancy centers. Yes, a colleague, Dr. Tanmay Basu, is leading that program.
Set of electron photonics.
This is photonics means it is. Yes, photons. Right, the photon. In this case, photonics, and this is the NV center work that we are doing. And these are some optical transitions they use to identify forms of the spin there. Connect those. Okay, maybe when you interact with the lab, you will see that. So this is photonic integrated circuit. It is almost like a Michelson interferometer. It's the 2 branches. You have a reference arm and something that you have to sense, a biological sample you can put there to get the response. These are the 2 things that Dr. Tanmay Basu is doing. And the quantum sensing with cold atoms, Dr. Rishi Kacharya is leading this program, that he measures this gravity. And these are the applications of measurements of G, submarine, research, seismic operation, navigation, subsurface mapping, so whether there is oil or minerals, other things, all this. So this is a collection of cold atoms. That's what it's showing. And here is a small video, it looks like. Something is a video of the MOT, magneto-optic trap. Atoms are trapped in that. Those are the labs. I mean, in the interaction section in the lab, you can go and see that. And this is the profile of the cold atom collection, the MOT. Superconducting qubit lab. That's where we are doing. This is the 1 qubit computer here. This is actually the reception junction that is shown here, and which is like the reception junction and capacitor LC circuit. And this is the qubit, as I said, that quantum system is fragile. It doesn't stay in the same one. So through this, we measure this oscillation between the two states called Rabi oscillation. You see this is gradually decaying. So that determines the lifetime of the qubit or the quantum system. And then, of course, interaction of this, the way we actually measure this state through the interaction with photons. And these photons are provided through this cavity, microwave cavity. And depending on the state of the qubit, the resonance frequency of the cavity shifts. We measure this shift to know the state of the quantum system. So this is the 5 qubit processor that is in. So whatever you see, these are the connection coupler, this is the resonator, all these things. This is how it is connected. And standard reception junctions use this structure, aluminum oxide aluminum. That's the tunnel junction. But there are huge problems, like they have oxide growth, and they provide this defects, and that defect reduces the lifetime of that. So we are working with a different material. For example, this oxidation, we are working with a different material that doesn't get oxidized. So with that, we have designed these resonators. Also, we are designing with qubit, and with that, we will also make the squeeze structure. So these are briefly the different activities. Okay.
For conductors.
Yeah. Yeah, we are making them. So there are posters for different activities, and also there are lab visits waiting.
Thank you, Professor Dev, for a nice illustrative talk and showing our brief activities. So now we'll have a short break for tea, and then we'll assemble for the facility visit and the interaction with the faculties. So during your registration, I hope you got a small token named A, B, C, D kind of things, right? So what we have planned that we will make 5 people a group. So let's say 5 A's will form a group, and then we have 7 posters specifically from theory related activities across our laboratory and office spaces. And then we have 3 laboratories. So sequentially we'll move to that so that you guys can interact with us, and we also can speak and interact with you. Or if you have any queries, you can talk to us. So if you have any queries, you please let us know. Or otherwise, we'll break the session here for the facility visit. And before closing, I wish all of you very happy Bengali New Year for tomorrow, and wish you all the best. Thank you. So we can meet outside there, and then I would request please help us to coordinate of a 5 small group, because the laboratories are specifically like a temperature controlled environment, so you cannot allow many people at once. So it will be better if